Imagine an object so powerful that it can outshine an entire galaxy, billions of stars, countless planets, all dwarfed by a single, incomprehensible beacon of energy. That's the staggering reality of quasars, the universe's most luminous and enigmatic phenomena. These cosmic powerhouses aren't just distant curiosities. They're windows into the extreme physics shaping our cosmos, defying everything we think we know about energy, time, and space itself. And the strangest part, the more we learn about them, the more questions they leave behind. At the heart of every quasar lies an active galactic nucleus, a supermassive black hole, millions or even billions of times heavier than our Sun, devouring matter at an unimaginable rate. But here's where things get bizarre. Instead of being hidden in darkness, these black holes become the brightest objects in existence. How the sheer violence of their feasting creates swirling disks of superheated gas, magnetic fields twisted into cosmic tornadoes, and jets of particles blasted across space at nearly the speed of light. It's like a cosmic storm we're only beginning to understand. Today, we're diving into 25 of the most mind-bending, spine-tingling mysteries surrounding quasars and active galactic nuclei. From their ability to warp space-time to the way they can literally rewrite the rules of physics, these phenomena challenge our very understanding of reality. You'll discover how quasars might hold clues to the birth of galaxies, why some appear to defy the limits of time, and what their eerie glow tells us about the fate of the universe itself. This isn't just a journey through space, it's a voyage to the edge of what's possible. So buckle up, the cosmos is about to get very, very strange. One of the most bewildering behaviors of quasars is their apparent ability to fling material across space faster than light itself, a phenomenon known as superluminal motion. At first glance, this seems impossible. Einstein's theory of relativity tells us nothing can surpass the speed of light, yet here we are, watching jets from quasars seemingly break that universal speed limit. The secret lies not in the laws of physics bending, but in the way our perspective plays tricks on us. These jets aren't actually outracing light. Instead, their motion creates a cosmic illusion. Imagine standing beside a highway at night, watching cars zoom past with their headlights on. If a car is racing toward you at nearly the speed of light, the light it emits would appear to arrive almost instantly, making the car seem like it's moving faster than reality. That's the key. Relativistic speeds distort our perception of time and distance. When quasar jets point almost directly at us, their near-light-speed motion, combined with the time delays of their emitted light, creates this astonishing optical effect. But the implications go deeper. Superluminal motion forces us to confront the mind-bending nature of relativity itself. The jets aren't breaking any rules, they're just revealing how space-time warps under extreme conditions. It's as if the universe is showing us a magic trick where angles and velocities conspire to make the impossible seem real. Even more fascinating, this illusion helps scientists measure the true speeds of these jets, confirming they still fall just short of light speed while appearing otherwise. What makes this phenomenon truly cosmic is its scale. These jets stretch for thousands of light years, threading through galaxies like luminous needles. Their apparent speed isn't just a quirk, it's a testament to the raw power of supermassive black holes, bending the very fabric of reality to their will. And while the illusion itself is well understood today, it serves as a humbling reminder. The universe always has another puzzle waiting just beyond our line of sight. If quasars are the universe's flashlights, blazars are its strobe lights flaring and fading with such dizzying speed. They rewrite the rules of cosmic patience. Picture this, an object billions of light years away, so colossal it could swallow solar systems whole, suddenly doubling or even tripling its brightness in the time it takes to brew a cup of coffee. That's the surreal reality of Blazar variability, where these active galactic nuclei don't just flicker, they rage against the very notion of stability. What makes this possible? The answer lies in their unique orientation. Blazars are quasars with a twist. Their relativistic jets point almost directly at Earth, turning their high-energy particle beams into cosmic searchlights aimed right at us. When turbulence ripples through those jets, maybe from clumps of matter spiraling into the black hole or magnetic fields snapping like rubber bands, the resulting shockwaves send bursts of light screaming across space. Because we're staring down the barrel of these jets, even tiny changes appear magnified, like watching a lighthouse beam flicker from a storm-tossed sea. But here's where it gets even stranger. The speed of these fluctuations acts like a cosmic stopwatch, revealing secrets about the blazar's hidden structure. If a blazar's brightness spikes in mere hours, physics dictates its energy source can't be larger than a few light hours across. Otherwise, the signal would smear out as it traveled. That means the hellscape powering these flares, whether it's the jet's base or a writhing knot of plasma, must be smaller than our solar system, yet pumping out more energy than entire galaxies. It's the ultimate contradiction, a cosmic titan operating on scales almost unimaginably tiny. Astronomers race to catch these outbursts using networks of telescopes spanning the globe because blazars refuse to wait. A flare spotted at dinner might vanish by breakfast, leaving only questions in its wake. And with each flicker, these cosmic enigmas force us to rethink how energy can be so concentrated, so volatile, and so defiantly unpredictable. The universe, it seems, has a flair for drama, and blazars are its most restless performers. When astronomers peer into the light of distant quasars, they sometimes find something that shouldn't be there. Spectral lines split cleanly down the middle, like a mirror reflecting light into twin peaks. These double-peaked emission lines are more than just a cosmic oddity. They're a fingerprint of chaos unfolding at the edge of a supermassive black hole. Normally, spectral lines appear as single, smooth curves, revealing the chemical makeup of gas swirling in the quasar's accretion disk. But when those lines fork into two distinct peaks, it's as if the universe is whispering a riddle we've yet to fully decode. One leading explanation points to the dizzying spin of the accretion disk itself. Picture a vinyl record spinning at near light speeds, with one side hurtling toward us while the other side races away. Gas on the approaching side gets Doppler shifted to shorter, bluer wavelengths, while gas on the receding side stretches to longer, redder ones. The result: a single spectral line torn apart, its twin peaks mapping the extreme rotation of a disk caught in the black hole's gravitational vise. But here's the twist: not all double-peaked lines fit this simple story. Some show asymmetries, kinks, or shifts that suggest something far stranger, like a second black hole dancing in the dark. This is where the binary black hole theory enters the stage. Imagine two supermassive black holes locked in a gravitational waltz, each dragging its own accretion disk along for the ride. Their orbital motion could warp and split spectral lines in ways a single disk never could, creating signatures that flicker over time as the giants circle one another. Finding such pairs would be a goldmine for astrophysics, offering a front-row seat to how black holes merge, a process that should shake space-time with gravitational waves. Yet proving their existence is maddeningly difficult. The distances are so vast, the scales so extreme, that even our best telescopes strain to separate the signal from the noise. And then there are the outliers, quasars, whose double peaks defy both explanations. Some show lines that change shape unpredictably, as if the disk were torn by turbulence or magnetically driven winds. Others hint at structures we've never seen, like spiral arms of gas or warped disks bent by relativistic effects. Each anomaly forces astronomers to ask, are we missing a piece of physics here? Could there be entirely new phenomena at play, hidden within these split lines? What makes this puzzle so thrilling is its stakes. Double-peaked lines aren't just quirks, they're probes into the most violent environments in existence. By deciphering them, we might finally understand how black holes feed, how they grow, and how they shape the galaxies around them. Every split line is a clue, and right now, the universe is daring us to put them together. Quasars are supposed to follow the cosmic rulebook. The farther away they are, the faster they're racing from us, their light stretched into longer, redder wavelengths by the expansion of the universe. But some of these cosmic beacons refuse to play by the rules. Their redshifts, the telltale fingerprints of their motion, don't match the galaxies they appear to call home. It's as if the universe handed us a map and then quietly scribbled errors all over it. Take the case of Quasar 3C186, a brilliant object embedded in a seemingly ordinary galaxy. The quasar's redshift suggests it's hurtling away at a staggering fraction of light speed, placing it billions of light-years distant, but the galaxy around it. Its stars and gas show a redshift that's far smaller, implying it's much closer. This mismatch isn't just a fluke, it's a full-blown cosmic contradiction. How can a quasar be so distant if its host galaxy isn't? Either something's wrong with our measurements or something far stranger is happening. One possibility is that these quasars aren't actually tied to their apparent hosts at all. Maybe they're cosmic hitchhikers lying far behind a foreground galaxy by pure chance alignment, but the odds of such perfect overlaps are astronomically low. Another explanation, these quasars might be getting a speed boost from invisible forces like supermassive black holes kicked out of their galaxies during violent collisions, now drifting through intergalactic space with their accretion disk still blazing. Imagine a bullet fired from a moving train. The quasar's redshift would carry both the train's motion and the bullet's extra kick. Then there's the radical idea that redshift itself might not always mean what we think. Could unknown physics, maybe interactions with dark matter or hidden dimensions, be tweaking the light from these objects? It's a controversial notion, but the anomalies keep piling up. Some quasars even exhibit multiple redshifts at once, as if their light is being filtered through layers of warped spacetime. The implications are staggering. If redshifts can't always be trusted, our cosmic distance ladder, the foundation of modern cosmology, might need recalibration. Entire galaxies could be closer or farther than we've assumed, rewriting the timeline of the universe's expansion. And lurking beneath it all is the haunting question: are we missing something fundamental about how light travels across the cosmos? Every anomalous quasar is a flare in the dark, urging us to look deeper, because the universe's greatest secrets often hide in its inconsistencies. Among the universe's quirkiest oddities, few stand out like the so-called green bean galaxies, cosmic specimens so strange they look like they've been dipped in neon paint. These aren't just any active galaxies, they're entire systems bathed in eerie, glowing green light, as if someone flipped a switch to illuminate their guts. And here's the kicker: that luminous haze isn't coming from stars. It's the ghostly aftermath of a quasar's tantrum, a fleeting phase in the life of an active galactic nucleus that we've only just begun to decode. The story of their discovery reads like a cosmic accident. Astronomers sifting through data from the Sloan Digital Sky Survey stumbled upon these emerald anomalies almost by chance. At first glance, they resembled ordinary galaxies hosting quasars until researchers noticed something peculiar. While quasars light up only their immediate surroundings, these galaxies were entirely aglow, their green hue stretching across tens of thousands of light-years. The culprit: ionized oxygen, a byproduct of intense radiation that had once flooded the galaxy, energizing gas far beyond the black hole's usual reach. It's as if the quasar had left the oven on and the whole cosmic kitchen was still simmering. What makes green beans so special isn't just their color, it's their role as cosmic time capsules. They're caught in a rare transitional phase, offering a snapshot of what happens when a quasar shuts off. Picture a lighthouse that's just been switched off, its beam gone but the air still buzzing with residual energy. That's a green bean, the afterglow of a dying AGN where the central black hole has stopped feeding ferociously, leaving the galaxy's gas to slowly fade back into darkness. The eerie green light is essentially a farewell note, a message from a black hole's final feast, but the real treasure lies in the timeline these galaxies reveal. Quasars are notoriously capricious, flickering on and off over millions of years. Green beans suggest the shutdown happens in stages, with radiation lingering long after the central engine sputters. Some astronomers think this could explain why so many dead quasars still show faint activity, like a campfire whose embers glow long after the flames die. And because the gas cools unevenly, these galaxies become natural laboratories for studying how energy dissipates across cosmic scales. There's also the tantalizing possibility that green beans hold clues to one of astronomy's biggest puzzles: how black holes and galaxies co-evolve. Their widespread ionization suggests quasars might sculpt their host galaxies not just through violent outbursts, but through subtler, lingering effects like a sculptor chiseling away long after the hammer stops striking. If that's true, these jade-hued oddities could rewrite how we think about the life cycles of galaxies themselves. Yet for all their intrigue, green beans are vanishingly rare. Out of millions of surveyed galaxies, only a handful fit the profile, making them cosmic needles in a haystack. That rarity hints they're fleeting, perhaps lasting just tens of thousands of years before their glow fades entirely. Catching one is like stumbling upon a fossil mid-formation, a moment frozen between life and extinction. And as astronomers race to study them, one thing's certain: these galaxies are more than just pretty colors. They're a glimpse into the universe's most dramatic metamorphoses, where even in death, light has the last word. Light doesn't always travel in a straight line, sometimes it bounces. And when the brilliant glare of a quasar strikes cosmic dust, the result is one of the most hauntingly beautiful phenomena in the universe: a light echo. Imagine shouting into a canyon and hearing your voice return seconds later, twisted by distance and terrain. Now replace the sound with light, the canyon with interstellar dust, and your voice with the scream of a supermassive black hole. That's a quasar's light echo, a delayed, distorted reflection that lets us peer into the hidden architecture of these cosmic monsters. The magic happens when a quasar's outburst, whether a sudden flare or a slow brightening, illuminates clouds of dust drifting light years away. The light takes extra time to reach us after ricocheting off those particles, creating a ghostly afterimage that lingers long after the initial flash. It's like watching lightning strike a distant mountain, then seeing the landscape flicker into view moments later. These echoes aren't just pretty, they're cosmic blueprints. By measuring the time delay and the echo's shape, astronomers can map the invisible scaffolding of dust and gas surrounding quasars, uncovering structures we'd never see otherwise. One of the most famous examples is Hani's Voorwerp, a glowing green cloud floating near the galaxy IC 2497. When Dutch schoolteacher Hanny van Arkel spotted it in 2007 while classifying galaxies online, it looked like a cosmic smudge, a mystery. But Hubble's keen eye later revealed the truth. The Voorwerp was a light echo illuminated by a quasar that had since dimmed. The light we see today left the quasar tens of thousands of years ago, bounced off the cloud, and is only now reaching us. The quasar itself has quieted, but its ghost still shines, a fossil of its former fury. What makes these echoes invaluable is their ability to freeze moments in time. A quasar's behavior can change over centuries, flaring, fading, or even shutting off entirely. But light echoes preserve snapshots of its past like cosmic photo albums. By studying multiple echoes, astronomers can reconstruct a quasar's history, tracing its outbursts across millennia. Some echoes even reveal the shape of the dust clouds they've illuminated, exposing vast rings, filaments, or spirals that would otherwise vanish into the dark. But there's a catch: light echoes are fleeting. As the original light fades and the dust disperses, the echo dims, vanishing over centuries or millennia. Catching one is like stumbling upon a shadow cast by a candle that burned out long ago. That's why missions like Hubble and the upcoming Nancy Grace Roman Space Telescope are crucial. They're time machines hunting for these whispers of ancient light before they disappear forever. And here's the kicker: some quasars might be surrounded by entire forests of echoes, each layer telling a different chapter of their violent lives. Imagine peeling back an onion, but instead of layers, you find staggered bursts of energy from a black hole's feeding frenzy. These echoes don't just illuminate dust, they illuminate history itself, revealing how quasars shape their galaxies over cosmic time. In the grand tapestry of the universe, light echoes are the loose threads that, when pulled, unravel stories we're only beginning to read. Two supermassive black holes locked in a gravitational dance, each weighing billions of suns, separated by less than the width of our solar system, should be impossible. Yet mounting evidence suggests these cosmic duos not only exist but may be hiding in plain sight within the hearts of active galaxies. The idea itself stretches our understanding of physics. Two space-time warping behemoths spiraling toward collision, their orbital tango so tight a single orbit might take just years instead of millennia. And when they finally merge, the resulting gravitational waves could shake the fabric of the universe itself. Take the bizarre case of OJ287, a Blazar flickering like a cosmic strobe light every 12 years like clockwork. These rhythmic outbursts aren't random, they're the smoking gun for a secondary black hole, roughly 150 times smaller, plunging through the primary's accretion disk like a bullet through water. Each pass triggers a violent splash of radiation, heating the disk until it screams in X-rays and gamma rays. It's the closest thing we have to watching a black hole demolition derby in real time, with each flare marking another lap in their death spiral. But confirming these binaries isn't easy. Their signatures are subtle slight wobbles in jet directions, periodic brightness changes, or telltale shifts in spectral lines that seem to rock back and forth as the black holes orbit. Some systems even exhibit double-peaked emission lines, where the gas in their accretion disks gets stretched and squeezed by competing gravitational forces, like taffy caught between two spinning wheels. The problem: at cosmic distances, these clues often blur into noise. A flicker might be turbulence, a spectral oddity could just be a warped disk. Even OJ287's clockwork flares have alternative explanations, like precessing jets or unstable magnetic fields. Yet the payoff for finding them would be astronomical. Binary supermassive black holes are the ultimate testbed for Einstein's theory of gravity. Their orbits, distorted by relativistic effects, could reveal secrets about how spacetime behaves under extreme strain. And when they collide millions of times louder in gravitational waves than stellar black hole mergers, they'd unleash ripples that future observatories like LISA might detect across the cosmos. These waves would carry fingerprints of the black hole's masses, spins, and even the shape of the space-time vortex they carved during their final moments. Perhaps most mind-bending is the timescale. A pair like OJ287's could orbit for millions of years before merging, their gradual in-spiral slowed by the very gas they're devouring. Some models suggest they stall just a light-year apart, trapped in a gravitational standoff until random stellar flybys or disk interactions nudge them closer. It's a reminder that even the universe's most violent events unfold with agonizing patience, and that somewhere out there, countless black hole pairs might be circling in the dark, waiting for their chance to make cosmic history. The hunt for these binaries is more than a curiosity, it's a window into how galaxies grow. If most large galaxies harbor central black holes, and if galaxies frequently merge, then binaries should litter the cosmos. Their absence would force us to rethink how black holes interact. Do they merge quickly, or does some unknown physics keep them apart? Every candidate system, from flickering blazars to X-ray bright quasars, is a piece of this puzzle. And with each discovery, we inch closer to answering one of astrophysics' biggest questions. What happens when two ultra-dense giants decide to tango? Quasars are supposed to be the universe's steady beacons, cosmic lighthouses burning with near-constant ferocity for millions of years. But astronomers have stumbled upon a bizarre subset that defies this expectation, flipping their identities almost overnight. These are the so-called changing-look quasars, celestial chameleons that transform from dazzling powerhouses to near-invisible ghosts in just months or years. It's as if someone flipped a switch inside these galactic cores, rewriting their very nature before our eyes, and the explanations range from violent black hole tantrums to cosmic curtains of dust. The first confirmed changing-look quasar, caught in 2015, left researchers stunned. Designated J015 plus 0625, it dimmed by a factor of 6 in under a decade, not just in brightness but in its spectral signature. The broad emission lines typical of quasars vanished, as if the accretion disk feeding the black hole had simply turned off. No gradual fade, no flickering warning. One moment it was a textbook quasar, the next it mimicked a mundane galaxy. The event forced astronomers to confront a radical idea. Supermassive black holes might not always feed at a steady pace. They could gorge and fast in cycles, with consequences that ripple across cosmic time. What triggers these transformations? One leading theory points to instabilities in the accretion disk itself. Picture a whirlpool draining a bathtub. If the water flow suddenly weakens, the vortex collapses. Similarly, if the steady stream of gas fueling a quasar gets disrupted, maybe by a passing star or a gravitational nudge from another black hole, the disk could fragment or dissipate, starving the black hole and dimming its fireworks. The process might even be self-correcting. As the disk cools, gas could clump and reignite in fall, restarting the quasar like a cosmic engine sputtering back to life. But there's a darker, dustier alternative. Some changing-look quasars may not be shutting off at all. They could be playing peekaboo behind thick clouds of dust. When immense filaments of sooty material drift across our line of sight, they can screen the quasar's brilliance, absorbing its visible and ultraviolet light while letting some infrared trickle through. The effect is eerily selective. From Earth, the quasar's spectrum appears to morph as different wavelengths get blocked, creating an illusion of transformation. It's the cosmic equivalent of watching a spotlight through shifting fog. One minute it's clear, the next it's gone. The most tantalizing cases, however, resist both explanations. Take J1027 plus 0049, which brightened and developed new emission lines in under 3 years, too fast for traditional disk instabilities, too precise for random dust. Some theorists speculate these wild swings could come from magnetically elevated disks, where tangled magnetic fields suddenly snap, flinging material inward in abrupt surges. Others ponder whether we're witnessing rare black hole binaries, where the companion's orbit periodically distorts the primary's disk, unleashing spasms of radiation. What makes changing-look quasars so revolutionary isn't just their fickleness, it's what they reveal about black hole diets. If quasars can flicker on and off like cosmic bulbs, then the universe's most energetic phenomena might be far more transient than we thought. Galaxies could spend millennia in quiet darkness, only to flare up when a fresh wave of gas drifts too close. It reshapes our understanding of how black holes grow, not in steady meals, but in unpredictable feasts and famines. And the implications stretch beyond individual objects. Surveys suggest up to half of all quasars might undergo these shifts over millennia, meaning today's brilliant beacons could be tomorrow's dim afterthoughts and vice versa. That volatility forces us to ask, how many dormant galaxies are just biding their time, hiding future quasars in their cores? The universe, it seems, loves a good plot twist, and changing-look quasars are its most dramatic sleight of hand yet. Imagine winds so powerful they could strip a galaxy naked, hurricanes of gas screaming outward at speeds approaching half the speed of light, carrying enough energy to bulldoze entire star systems. These aren't cosmic metaphors, they're ultra-fast outflows, some of the most extreme phenomena unleashed by active galactic nuclei. While quasars dazzle us with their brilliance, these invisible gales do the real heavy lifting, sculpting galaxies with forces so vast they defy comprehension. At their core, ultra-fast outflows are superheated tsunamis of ionized gas, blasted from the accretion disk around a supermassive black hole. Think of them as the black hole's indigestion, excess energy too furious to stay confined. Magnetic fields twist like rubber bands, particle jets carve escape routes, and radiation pressure cooks gas until it erupts outward at millions of miles per hour. But here's the twist, these outflows don't just dissipate into the void. They ram into the galaxy's own gas reservoirs, triggering shockwaves that ripple across thousands of light years. The effect is cosmic gardening on a grand scale, either pruning star-forming clouds or uprooting them entirely. One stunning example comes from the quasar PDS 456, where astronomers clocked an outflow tearing through space at roughly 1/5 light speed. At that velocity, the gas could cross the entire Milky Way in less than 100,000 years, a blink in cosmic time. But what's truly shocking is the sheer force behind it. This single outflow carries more kinetic energy per year than the Sun will emit in its entire 10 billion-year lifespan. Multiply that across millions of years, and you've got a recipe for galactic transformation. The implications are staggering. These outflows solve a mystery that's puzzled astronomers for decades: why some massive galaxies quench, shutting down star formation despite having plenty of gas. The answer: their central black holes act like cosmic fire extinguishers. As outflows slam into interstellar gas, they heat it to extremes or blast it clean out of the galaxy. Without dense, cool gas clouds to collapse into stars, these galaxies become celestial graveyards littered with aging stars but devoid of new ones. It's a brutal feedback loop. The hungrier the black hole, the stronger its outflows, and the more effectively it strangles its own galaxy's future. Yet there's a paradoxical beauty to this violence. Without ultra-fast outflows, galaxies like ours might never have formed. Early in the universe's history, unchecked star formation could have turned galaxies into overcrowded stellar metropolises, burning through fuel too quickly. By regulating star birth, these outflows may have allowed galaxies to evolve more sustainably, like a cosmic pressure valve ensuring balance. Some theories even suggest that the gas expelled by outflows eventually rains back down in cooler streams, fueling new generations of stars in a cycle of destruction and rebirth. Detecting these invisible tempests isn't easy. Unlike quasar jets, which shine brightly, outflows often reveal themselves only through subtle fingerprints in X-ray spectra, slight absorption lines where speeding gas has stolen specific wavelengths of light. It's like identifying a hurricane by the faint shadow it casts on a spotlight. But missions like Chandra and XMM Newton have turned these spectral whispers into maps, tracing outflows across the cosmos. The more we look, the more we realize these winds are everywhere, not just in quasars but in quieter, active galaxies too, each contributing to the grand choreography of galactic evolution. What makes ultra-fast outflows truly humbling is their duality. They're both destroyers and architects, capable of sterilizing a galaxy or setting the stage for its next act. In their fury, they weave the invisible threads connecting black holes to the galaxies they inhabit, proof that even the universe's most violent phenomena are part of a delicate, balanced equation. And as we piece together their role, one thing becomes clear: the cosmos doesn't just build with light and gravity. Sometimes it sculpts with wind. Black holes come in two flavors we know well: the stellar mass leftovers of dead stars and the supermassive behemoths lurking in galactic cores. But where are the middle children? The universe seems to have skipped a generation. leaving a glaring gap between black holes weighing thousands of suns and those packing billions. This absence isn't just odd, it's a cosmic whodunit with active galactic nuclei as the crime scene. If supermassive black holes grew from smaller seeds, why are intermediate mass black holes so shockingly rare in AGNs? One clue lies in the feeding frenzy required to build a supermassive monster. Picture a black hole as a fire. The more you feed it, the faster it grows. Stellar mass black holes start small, but in dense environments like globular clusters or galactic centers, they might gorge on gas, stars, or even other black holes, bulking up over time. Yet somehow, this process leaves behind almost no traces of black holes in the 1,000 to million solar mass range. It's like finding skyscrapers and cottages but no apartment buildings, a glaring omission in the cosmic real estate market. Theories abound. Maybe intermediate mass black holes do exist but disguise themselves too well. Unlike their supermassive cousins, they might not accrete enough gas to shine brightly as AGNs, slipping under the radar of telescopes. Or perhaps they form in places we've barely searched, like the outskirts of galaxies, where collisions between smaller black holes could quietly birth middleweights without the fanfare of an accretion disk. There's even a chance they're cannibalized too quickly, swallowed by supermassive black holes before they can leave a detectable footprint. The hunt for these missing giants has turned up a few tantalizing candidates. Take HLX-1, an ultra-luminous X-ray source in a distant galaxy, whose energy output suggests a black hole of roughly 20,000 solar masses. Then there's the bizarre object in the galaxy Messier 82, flickering with X-rays that hint at a black hole too large to be stellar but too small to be supermassive. Yet these detections are exceptions, not rules. For every potential intermediate mass black hole found, thousands of AGNs glare at us with only supermassive or tiny black holes in their cores. The implications ripple across cosmology. If intermediate stages are truly scarce, it could mean supermassive black holes didn't grow gradually but formed through extraordinary leaps. Perhaps from direct collapse, black holes born already massive in the early universe. Alternatively, the growth process might involve mergers so chaotic that middleweights rarely stick around long enough to be observed. Every undetected intermediate mass black hole isn't just a missing link, it's a question mark hovering over our models of galactic evolution. What makes this mystery so urgent is its connection to the universe's first black holes. Did they start small and grow steadily, or were they born colossal, skipping intermediate stages entirely? AGNs should hold the answer, but until we find more middleweights, the puzzle remains unsolved. The cosmos, it seems, loves keeping its receipts buried. And in this case, the missing numbers might rewrite the story of how black holes, and the galaxies they anchor, came to be. The cosmos is threaded with an invisible web, vast filaments of dark matter stretching between galaxies like cosmic highways, punctuated by immense voids where almost nothing exists. Quasars, those brilliant beacons powered by ravenous black holes, should be scattered randomly across this web. Yet something strange is happening. A curious number of them seem to be lining up with these large-scale structures, as if their activity is somehow tied to the universe's hidden architecture. It's not just a coincidence, it's a clue that the environment around a quasar might play a far bigger role in its behavior than we ever imagined. Take the Sloan Great Wall, one of the most colossal structures in the observable universe, a sprawling filament of galaxies over 1 billion light-years long. When astronomers mapped quasars near this megastructure, they noticed an eerie trend. Many aligned along its spine like pearls on a string, their jets pointed parallel to the filament's axis. Meanwhile, quasars inside cosmic voids, those desolate, galaxy-poor regions, often flicker differently, with slower variability and weaker emission lines. The pattern suggests that where a quasar lives in the cosmic web might determine how it feeds, flares, and evolves. Scientists call this the alignment problem, and it's sparking fierce debate. One camp argues it's all about gas supply. Filaments are dense with intergalactic hydrogen, funneling fuel toward galaxies and their central black holes like rivers feeding a lake. A quasar in such a traffic jam would feast constantly, its accretion disk stable and bright. But in voids where gas is scarce, black holes might starve, sputtering with erratic flares as they scrape together scraps. That would explain why void quasars seem moodier, they're running on fumes. Yet there's a twist. Some aligned quasars show jet directions that match the spin axes of their host galaxies too precisely for randomness. That hints at something deeper, like the filament's gravitational torque gently nudging the galaxy's rotation into harmony with the cosmic flow. Imagine a leaf caught in a stream aligning with the current. Over billions of years, galaxies might be sculpted by these vast tidal forces, their black holes inheriting their orientation from the universe itself. If true, quasars aren't just passive residents of the cosmic web, they're products of it. But not all evidence fits neatly. Some studies find quasars aligned perpendicular to filaments, their jets blasting directly into the void. Others show no alignment at all. The inconsistency has led to wilder theories like dark matter interactions influencing black hole spin, or primordial magnetic fields woven into the cosmic web redirecting jets like cosmic weather vanes. Even the legendary axis of evil, a purported large-scale directional anomaly in the cosmic microwave background, has been dragged into the debate. Could the universe have a preferred direction that shapes quasars? The data isn't conclusive, but the mere possibility sends shivers down the spines of cosmologists. What makes this mystery so pivotal is its scale. If quasars truly align with the cosmic web, it means black holes billions of light-years apart are obeying the same environmental rules, a synchronization that defies intuition. It would imply that the universe doesn't just build structures, it orchestrates how energy flows through them. And tucked within that revelation is an even deeper truth. Quasars might not be isolated monsters. They could be weather vanes pointing us toward the invisible forces that shaped everything. Quasars might all look like cosmic spotlights at first glance, but their secret lies in what they don't show. Some blast radio waves across the universe like celestial sirens, while others stay eerily silent, no static, no hum, just the quiet glow of visible light. This split between radio loud and radio quiet quasars isn't just a technicality. It's a fundamental divide that could reveal how black holes harness energy, why jets form, and even how galaxies evolve. Take the archetypal radio loud Quasar 3C273, a powerhouse with jets stretching millions of light-years visible even to amateur telescopes. Then there's its radio-quiet cousin, like PG0043 plus 039, shining just as brightly in optical light but virtually mute in radio frequencies. The difference isn't about raw power, both might have similarly massive black holes. Instead, it's about how those black holes channel their fury. Radio-loud quasars seem to focus energy into narrow, magnetized jets, while radio-quiet ones radiate more isotropically, like light bulbs without a directional beam. So what tips the scales? One key player is the black hole's spin. Think of a spinning top versus a stationary one. The rotating version stores energy in its motion. For black holes, rapid spin twists magnetic fields into a coiled spring, launching jets along the rotation axis like cosmic artillery. Simulations show that while all supermassive black holes likely spin, radio-loud quasars might spin faster, their magnetic fields wound tighter by the whirlpool of infalling gas. But spin alone doesn't explain everything. Some radio-loud quasars have oddly sluggish spins, while a few radio-quiet ones twirl rapidly. That's where magnetic fields step in. Imagine a black hole's accretion disk as a dynamo. Turbulence in the disk generates magnetic fields, which can either stabilize into jet-launching mechanisms or tangle into inefficiency. Radio-loud quasars might have cleaner, disks-less clumpy gas, smoother magnetic geometries allowing fields to align and catapult particles outward. Radio-quiet quasars, by contrast, could suffer from magnetic chaos, their fields knotting and reconnecting before jets can form. It's the difference between a fire hose and a sprinkler. Both eject water, but only one does it with precision. Yet the plot thickens when you consider their host galaxies. Radio-loud quasars often live in elliptical galaxies, where mergers have funneled gas efficiently to the core, possibly spinning up the black hole. Radio-quiet quasars prefer spiral galaxies, where gas trickles in more erratically. This hints that environment might load the dice. Certain galactic conditions favor jet production, while others leave black holes quiet even as they feast. The consequences ripple across cosmology. Radio-loud quasars with their jets can inject energy into intergalactic space for billions of years, heating gas and suppressing star formation. Radio-quiet ones might influence their surroundings more subtly, their radiation gently sculpting nearby clouds. Both are cosmic engines just running on different blueprints. And that's the real mystery: why the universe built two versions of the same monster. Is it chance, physics, or some deeper rule we've yet to uncover? For now, the silence of one class speaks as loudly as the roar of the other. Quasars don't die quietly. Some go out with a whimper, others with a bang, and a few even come roaring back to life like cosmic zombies. The idea that these luminous monsters could flicker on and off challenges everything we thought we knew about black holes as steady, insatiable beasts. But the evidence is undeniable. Quasars do shut down, sometimes for millions of years, only to reignite in violent rebirths. The question is, what flips the switch? One leading theory points to a delicate balancing act between feeding and feedback. Picture a black hole as a fire. Feed it too much gas and it blazes brightly as a quasar. But that brilliance comes at a cost. Radiation and jets from the active nucleus can heat surrounding gas to such extremes that it billows outward, starving the black hole of fresh fuel. It's like a wildfire that burns so hot it destroys its own fuel supply, leaving only embers. This self-regulating cycle could explain why some quasars dim suddenly, their accretion disks evaporated by their own fury. But nature has a way of restocking the pantry. Enter tidal disruption events, cosmic catastrophes where a star wanders too close to a dormant supermassive black hole and gets shredded into a spaghetti-like stream of gas. The sudden influx of fresh material can jolt the black hole awake, igniting a short-lived quasar phase as it feasts on the stellar debris. In 2011, astronomers witnessed this firsthand when a previously quiet galaxy, Swift J1644+57, flared into a quasar after devouring a star. The event was a smoking gun, proof that black holes can lurk in darkness for eons, only to be resurrected by random acts of violence. Yet some quasars cycle on and off without such dramatic triggers. Simulations suggest that accretion disks aren't smooth, steady flows but clumpy, chaotic whirlpools. Dense knots of gas might spiral inward in bursts, causing the quasar to brighten episodically, while quieter periods reflect gaps in the menu. It's like a sink with a clogged drain water pools until pressure clears the blockage, then rushes out in a surge. For quasars, these clumpy accretion models could explain why some flicker unpredictably, their light curves spiking and plunging like a strobe light in slow motion. Then there's the grandest reboot of all, galaxy collisions. When two galaxies merge, their central black holes eventually spiral together. But first, the encounter funnels vast reservoirs of gas toward the cores. A dormant black hole suddenly finds itself at an all-you-can-eat buffet, flaring into a quasar as it gorges. This might explain why quasars were more common in the early universe. Galaxies crashed together more frequently, keeping black holes perpetually stuffed. Today, mergers are rarer, leaving many black holes fasting in the dark. The most tantalizing clue comes from Phoenix Quasars systems where cold gas, previously blasted away by outflows, later cools and falls back into the galactic center, reigniting the black hole's engine. It's a cosmic version of rain refilling a dried-up lake, proving that even the most violent feedback loops can reverse. These rebirths suggest quasar activity isn't linear but cyclical, with galaxies oscillating between frenzy and famine over cosmic timescales. What makes this cycle so pivotal is its role in shaping galaxies. Each quasar phase injects energy into the surrounding galaxy, heating gas or flinging it outward, while dormancy allows gas to settle and cool. This push and pull could regulate star formation, ensuring galaxies don't burn out too quickly. The universe, it seems, has built an off switch for its most powerful engines, not to silence them forever, but to let them breathe, reset, and roar back to life when the time is right. And somewhere out there, countless black holes wait in the dark, their next awakening just a matter of time. Staring at the light from a quasar, astronomers noticed something peculiar. The brighter the quasar, the weaker one particular emission line appeared in its spectrum. This counterintuitive trend, known as the Baldwin effect, flips expectations on their head. You'd assume a more luminous quasar would have stronger emission lines, not fainter ones. Yet this inverse relationship isn't a fluke. It's a powerful clue about the inner workings of active galactic nuclei, revealing secrets about their structure, radiation, and even how they evolve over cosmic time. The effect centers on a specific spectral line called C4, emitted by ionized carbon atoms in the quasar's broadline region, the turbulent zone of gas swirling near the black hole. As quasars grow brighter, the C4 line weakens, almost as if the gas responsible for it is being drowned out by the quasar's own brilliance. One explanation points to changes in the ionizing radiation pouring from the accretion disk. In dimmer quasars, the radiation field is softer, allowing carbon atoms to retain some of their electrons and emit C4 strongly. But crank up the luminosity, and the flood of high-energy photons strips carbon atoms bare, leaving fewer electrons available to produce the line. It's like turning up a spotlight so bright that shadows vanish entirely. The very conditions needed to create the line get erased by the quasar's intensity. Yet the Baldwin effect isn't just about radiation physics. It might also trace the geometry of the quasar's inner sanctum. Some models suggest that brighter quasars have more radiation escaping along their poles, leaving less to interact with gas in the broadline region. Imagine a flashlight pointed straight at you. Its beam seems intense, but the light spraying sideways is weaker. Similarly, a quasar's orientation could determine how much energy spills into the gas clouds that produce C4, subtly altering the line's strength. This would mean the Baldwin effect isn't just about power, it's about perspective, with the same quasar appearing different depending on how we view it. The plot thickens when you consider time. The Baldwin effect seems to evolve with redshift, meaning it changes as we look back to earlier cosmic epochs. High redshift quasars, those billions of light years away, show a steeper drop in C4 strength with luminosity than their local counterparts. This could hint that ancient quasars had different broad-line regions, perhaps more compact, more energetic, or bathed in harder radiation than today's versions. If true, the Baldwin effect becomes a cosmic clock, tracking how black holes and their feeding mechanisms have transformed over the age of the universe. But there's a twist. Not all emission lines obey this rule. Some, like Lyman alpha, barely respond to changes in luminosity, while others, like magnesium, follow their own trends. These outliers suggest the broadline region isn't a uniform shell of gas but a layered, complex structure where different lines form at different distances from the black hole. The Baldwin effect, then, isn't just one phenomenon, it's a mosaic of processes, each exposing a different slice of the quasar's anatomy. What makes this discovery so revolutionary is its simplicity. Unlike flickering jets or shifting spectral lines, the Baldwin effect is a quiet, persistent pattern, a whisper in the data that echoes across millions of quasars. By decoding it, astronomers aren't just reading a spectral line, they're reconstructing the invisible physics of the universe's most energetic engines. And in that faint, fading signal, they've found a new way to measure the cosmos one photon at a time. Sometimes the universe itself becomes a magnifying glass, bending light in ways that reveal secrets we could never see directly. Quasar microlensing is one of those rare cosmic tricks where a star, planet, or even a rogue black hole drifting in front of a distant quasar acts like a natural lens, warping and amplifying its light in unpredictable flickers. Unlike the steady glow we usually observe, these chance alignments create bizarre, ever-changing brightness patterns, as if someone were twisting a telescope's focus knob at random. But buried in that chaos is a goldmine of information about quasars' hidden structures and the invisible dark matter weaving through galaxies. Here's how it works. Imagine a quasar's accretion disk, a swirling maelstrom of superheated gas emitting light that travels billions of light-years toward Earth. Along the way, a single star in a foreground galaxy passes almost perfectly between us and the quasar. Einstein's general relativity tells us that the star's gravity bends spacetime, creating a tiny lens that distorts and magnifies the quasar's light. But because the star is moving, the magnification flickers unpredictably, sometimes brightening one part of the disk, sometimes another. It's like holding a magnifying glass over a glowing ember while running. The ember's light dances and flares as the lens jitters. What makes microlensing so powerful is its resolution. Even our sharpest telescopes can't directly see a quasar's accretion disk. It's too small and too far away. But microlensing effectively scans the disk as the foreground star moves, revealing hotspots, asymmetries, or even spiral structures in the gas. In 2014, researchers studying the quasar RxJ1131-1231 caught a microlensing event that exposed something startling. The disk's inner edge was far hotter than models predicted, suggesting the black hole's spin was warping spacetime so severely that gas piled up in a searing ring. Without microlensing, we'd never have spotted that detail, but the real magic lies in the shadows. Most of the matter in the universe is dark, invisible to telescopes. Yet when dark matter clumps around a lensing galaxy, it subtly alters the microlensing pattern. By tracking how quasars flicker during these events, astronomers can map the unseen mass between us and the quasar, like tracing the outline of a hidden object by watching how it bends light. Some microlensing anomalies even hint at free-floating black holes or rogue planets drifting between galaxies, objects otherwise impossible to detect. The catch: microlensing is mercilessly unpredictable. Events can last days or decades, and no two are alike. A quasar might flare unexpectedly, then vanish back into obscurity before telescopes can swing into action. That's why projects like Ogle and Gaia keep relentless watch, scanning millions of quasars for the telltale twinkles that betray a lensing event in progress. Every flicker is a message in a bottle carrying clues about the quasar's heart, the galaxy in front of it, and the dark matter threading the cosmic web. And sometimes, just sometimes, the universe lines up perfectly to let us read it. Quasars aren't supposed to flicker like candles. These cosmic powerhouses should burn with near-constant ferocity. They're supermassive black holes feeding on a steady diet of gas. Yet some active galactic nuclei defy expectation, flaring and dimming erratically over days or even hours. These rapid, small-scale brightness changes aren't just random noise. They're windows into the chaotic whirlpool of matter spiraling toward oblivion, where turbulence and clumps rewrite the rules of accretion physics. Take the case of Ferrol 9, a seemingly ordinary active galaxy that stunned astronomers by doubling its X-ray brightness in under 27 hours. The event wasn't a tidal disruption or jet ejection, just the black hole's inner disk throwing a tantrum. Such swift swings point to processes unfolding in regions smaller than our solar system, where gas doesn't flow smoothly but arrives in unpredictable waves. Imagine trying to predict the flickers of a bonfire by watching logs tossed haphazardly into the flames. That's the challenge of modeling these AGN variations. What drives this frenzy? One leading theory blames magnetorotational instability, where magnetic fields tangled in the disk create pockets of turbulence. Gas spirals inward faster in some zones than others, clumping into dense knots that heat violently before dissolving. Like bubbles bursting in boiling water, these ephemeral hotspots flare briefly before vanishing, their combined flickering making the entire quasar appear unsteady. Supporting this idea, simulations show clumpy disks naturally produce the flickering patterns we observe right down to the telltale red noise, where small fluctuations ride atop larger, slower waves. Yet there's a competing explanation: disk tears. As gas orbits the black hole, relativistic effects can warp the inner disk into misaligned rings that grind against each other. These collisions release bursts of energy like tectonic plates slipping in an earthquake. The result: sharp, erratic spikes in brightness as the disk literally shears itself apart. Some observed flickers even match predicted timescales for these disk-breaking events, offering tantalizing evidence that black holes don't just consume matter, they shred it violently first. The most extreme cases push physics to its limits. The AGN in galaxy GSN 069, for instance, dims by nearly 20% in just 36 hours, a drop requiring the inner disk to cool catastrophically fast. Traditional physics struggles to explain how a region so dense could shed heat so quickly, leading to wilder theories like runaway magnetic reconnection or even quantum effects near the event horizon. It's as if the black hole's dining habits switch between a gourmet meal and a frenzied snack without warning. What makes these flickers invaluable is their diagnostic power. Just as a doctor listens to a heartbeat, astronomers use brightness variations to probe the accretion disk structure. Rapid flickers likely originate close to the black hole, where orbital speeds approach light speed, while slower changes trace the disk's colder outer reaches. By untangling these signals, researchers can map unseen features, like the plunging region where gas stops circling and plummets inward, or the elusive corona of superheated electrons hovering above the disk. The implications stretch beyond single black holes. If flickering reflects universal accretion physics, then similar patterns should appear in smaller systems like stellar mass black holes or even protoplanetary disks. Remarkably, they do. The scaled-down flickers of microquasars like GRS 1915 plus 105 mirror their supermassive cousins, suggesting a cosmic unity in how matter falls onto compact objects. From star-forming clouds to galaxy cores, turbulence and clumpiness might govern growth across the universe. Yet for all we've learned, AGN flickering remains maddeningly unpredictable. No two quasars vary exactly alike, and attempts to forecast their behavior often fail, a reminder that near black holes chaos reigns supreme. Each erratic pulse is both a message and a riddle, carrying secrets of spacetime's edge in bursts of light we're only beginning to decode. And as telescopes grow sharper, these cosmic winks may yet reveal the universe's most volatile dining rooms in unprecedented detail. The earliest quasars weren't just younger versions of the monsters we see today. They were something else entirely, blazing to life in a universe barely out of its cosmic cradle. Finding quasars shining less than 700 million years after the Big Bang poses a staggering puzzle. How did supermassive black holes grow so massive so fast? These weren't just bright objects, they were cosmic overachievers, defying the laws of physics as we know them. The answer might lie in a radical idea that the first quasars didn't grow from humble beginnings but were born giants, forged in the collapse of primordial gas clouds so dense they skipped the star-making stage entirely. Picture the early universe, a seething cauldron of hydrogen and helium, devoid of heavy elements where gas pooled in deep gravitational wells. Under normal circumstances, such clouds would fragment into stars, but in these pristine conditions, something extraordinary could happen. Without dust or metals to cool the gas efficiently, immense clouds weighing tens of thousands of suns might have collapsed directly into black holes. No supernova, no stellar remnant, just a raw gravitational free fall creating a seed already thousands of times heavier than today's stellar mass black holes. These direct collapse black holes would have had a head start, feasting on the surrounding gas to balloon into supermassive status within a few 100 million years. It's the cosmic equivalent of a baby born fully grown skipping adolescence entirely. Evidence for this wild scenario comes from the most distant quasars we've found, like J034-5145, shining when the universe was just 670 million years old. Its black hole weighs over 1 billion solar masses, an impossible feat if it grew from a single star's collapse. Even devouring gas at the maximum theoretical rate, a stellar mass seed wouldn't have had enough time. Unless, of course, it started as something far larger. Simulations show these direct collapse seeds could form in rare, ultra-dense regions where ultraviolet light from neighboring galaxies prevented gas from splitting into stars, leaving it all to funnel into a single, monstrous pit. But direct collapse isn't the only contender. Some theories suggest black holes could have grown faster than expected by gorging on streams of cold gas funneled along cosmic filaments like rivers feeding a reservoir. Others propose that early black holes merged at unprecedented rates, their collisions turbocharging growth in the crowded infant universe. There's even the controversial notion that primordial black holes forged in the Big Bang's chaos could have provided ready-made seeds. Each model has its flaws. Gas streams might not deliver enough material, mergers take time, and primordial black holes remain purely hypothetical. Yet the existence of those ancient quasars demands an explanation. What makes these progenitor quasars so fascinating is their legacy. The light we see from them today is a snapshot of their youth, but their influence stretches across cosmic time. Their radiation helped reionize the universe, stripping electrons from hydrogen atoms and ending the cosmic dark ages. Their outflows seeded galaxies with heavy elements, and their gravitational pulls may have shaped the first large-scale structures. They weren't just luminous oddities, they were architects carving the universe into the form we recognize today, and the hunt for their origins is far from over. Telescopes like JWST are peering deeper into the infrared, searching for black holes in the process of formation, ones too young to yet shine as quasars. Others scan for the chemical fingerprints of direct collapse, like galaxies bizarrely deficient in heavy elements, hinting at a place where stars never formed. Every new discovery tightens the noose around these cosmic mysteries, but the early universe guards its secrets fiercely. One thing's certain, the first quasars weren't just brighter. They were fundamentally different beasts born from a universe so alien, even their shadows rewrite the rules. Light isn't just about brightness, it's about direction. And when it comes to blazars, some of the most violent objects in the universe, the way their light twists and turns holds secrets about the invisible forces shaping their jets. Polarized light waves vibrating in a preferred direction acts like a cosmic compass, pointing straight to the tangled magnetic fields whipping particles to near light speeds. Take Markarian 421, a blazar so intense it can outshine entire galaxies. When astronomers analyzed its polarized light, they found something astonishing. The polarization angle didn't just drift, it rotated in sweeping, predictable cycles. This wasn't random chaos, it was the signature of a magnetic helix, a coiled spring of energy winding through the jet like a corkscrew. Imagine a garden hose thrashing as water gushes out. The spiral motion leaves its mark in the light, revealing structures too small for any telescope to resolve directly. But polarization does more than map magnetic fields, it tracks shocks. Blazar jets aren't smooth rivers of particles. They're choppy with internal collisions, where clumps of plasma slam into each other, unleashing bursts of gamma rays. Each shockwave sends a ripple through the jet's magnetic field, imprinting a sudden shift in polarization. In 2017, Markarian 421's gamma ray flare coincided perfectly with a 90-degree polarization swing, proving these shocks are real and violent. It's like catching a sonic boom in starlight. The moment kinetic energy becomes visible, the real magic happens when polarization meets physics. Some blazars show circular polarization, a spiraling twist in the light that hints at electrons gyrating in magnetic fields. Others flicker between polarized and unpolarized states, suggesting their jets aren't monolithic but fragmented, with turbulent cells battling for dominance. These patterns aren't just academic, they're clues about how black holes launch jets in the first place. If polarization stays orderly over long distances, the jet's magnetic field might be frozen in, sculpted by the black hole's spin. If it scatters wildly, the jet could be shredding itself from within. Then there's the mystery of the polarization hole, a bizarre drop in polarization during some flares. One theory blames beam dilution. Fresh plasma surging into the jet temporarily drowns out the organized magnetic signal, like static overwhelming a radio station. Another posits magnetic reconnection, where field lines snap and rearrange, briefly scrambling the polarization before settling into new alignments. These hiccups aren't glitches, they're glimpses into the jet's engine room, where energy transforms from magnetic to kinetic in a heartbeat. What makes polarized light so powerful is its honesty. Unlike brightness, which can deceive with distance or absorption, polarization carries fingerprints of the processes that created it. By reading these subtle twists, astronomers have reconstructed blazar jets in ways no image could, mapping their magnetic skeletons, timing their shocks, even weighing their particle content. And with every new observation, the message grows clearer. Behind the glare of these cosmic monsters, the universe is writing its secrets in angles and vibrations, waiting for us to decipher the code. Quasars might seem like a chaotic menagerie of cosmic monsters, each blazing with its own unique fury, but hidden beneath their wild variations lies an invisible order. Astronomers call it the Quasar main sequence, a classification system that sorts these luminous beasts by the subtle fingerprints in their light, revealing patterns as profound as the periodic table is for chemistry. What started as a simple way to categorize quasars has blossomed into a revolutionary framework, reshaping how we understand the inner workings of active galactic nuclei and the black holes that power them. At the heart of this system are two key measurements: the width of a quasar's hydrogen beta emission line and the ratio of iron to oxygen emission strength. These might sound like obscure details, but together they paint a vivid portrait of a quasar's structure and behavior. Narrow hydrogen beta lines, for instance, often trace back to slowly spinning black holes with thicker, puffier accretion disks, while broader lines hint at faster spins and thinner, hotter disks. It's the difference between a lazy whirlpool and a raging vortex, the same basic physics, but scaled to extremes. Meanwhile, the iron-to-oxygen ratio acts like a cosmic speedometer, tracking how intensely the black hole is feeding. More iron suggests a richer, more metal-loaded diet, often tied to galaxies that have cycled through generations of star formation before funneling gas to their cores. What makes the sequence so powerful is its predictive power. Just as Mendeleev's periodic table left gaps for undiscovered elements, the quasar main sequence has empty zones that point to theoretically possible but still unobserved quasar configurations. Some of these gaps have since been filled, like the discovery of weak-line quasars that glow fiercely in X-rays but barely whisper in optical emission lines. These outliers challenge old assumptions, proving that black holes can shine brightly even when their accretion disks are oddly inefficient at producing certain types of light. The sequence also reveals an unseen hierarchy among quasars. At one end sit populated objects with strong, broad emission lines, classic high-energy monsters like 3C273. At the other end are shadowed quasars, their light dimmed by thick shrouds of dust, detectable only in infrared or X-rays. Between them lies a spectrum of hybrids, each with its own balance of radiation and obscuration. This continuum suggests that what we call a quasar might not be a single type of object but a phase in a black hole's life cycle, one that changes as it gorges, feedbacks, and interacts with its host galaxy. Perhaps most intriguing is how the sequence bridges theory and observation. Simulations of accretion disks now aim not just to replicate quasar light, but to slot their virtual creations precisely onto the main sequence's grid. When a simulation's predictions align with real-world data, it's a sign that the underlying physics, the turbulence of magnetized gas, the dance of radiation pressure, is being captured correctly. It's like testing a flight simulator by checking if it produces realistic turbulence, not just smooth cruising. But the sequence isn't static. Recent work hints at a second dimension to the taxonomy, where a quasar's position also reflects the viewing angle to its jet. Face-on quasars might appear fundamentally different from those seen edge-on, their light filtered through varying depths of obscuring material. This added layer turns the main sequence from a flat chart into a dynamic 3D map, one that could eventually include every active galaxy in the universe, from the brightest Blazars to the faintest Seyferts. What began as a sorting tool is now a Rosetta Stone for decoding black hole behavior. By reading the patterns in quasar light, astronomers can infer spin rates, feeding states, and even the chemical history of their host galaxies, all without resolving a single disk. The quasar main sequence doesn't just organize chaos, it reveals the hidden logic behind the universe's most dazzling engines, proving that even in the maelstrom of a supermassive black hole, there's method to the madness. Some of the universe's most powerful monsters don't want to be seen. Lurking behind thick curtains of dust, these hidden quasars, known as obscured active galactic nuclei, shine not in visible light but in X-rays and infrared, their brilliance filtered through cosmic silt. To the unaided eye, they might look like ordinary galaxies or even dim nothingness. Yet peel back the dust and you'll find engines just as ferocious as their dazzling counterparts, rewriting the rules of how black holes shape and hide within their galaxies. The key to uncovering these giants lies in the light they can't suppress. Dust absorbs visible and ultraviolet radiation, but high-energy X-rays punch through, revealing the searing temperatures near the black hole's maw. Infrared, meanwhile, betrays the dust itself, glowing with the heat of absorbed quasar light re-radiated at longer wavelengths. It's like spotting a lighthouse through fog. The beam might be dimmed, but the gleam of the mist tells you something powerful lies behind. Take NGC 1068, a seemingly mundane galaxy until X-ray observatories exposed its core blazing with the energy of a fully fledged AGN. Its visible light smothered under 10,000 solar masses of dust. This duality isn't random, it's foundational to the unified model of active galaxies. The model proposes that all AGNs are fundamentally the same beast, their apparent differences arising simply from our viewing angle. Face a quasar's jet head-on and you see a blistering Blazar. View it sideways through the dusty torus surrounding the black hole, and it becomes an obscured AGN. The same powerhouse, just wearing different cosmic disguises. The implications are profound. What we once classified as distinct objects, Seyfert galaxies, quasars, radio galaxies, might all be siblings in a single family, their diversity an illusion of perspective. Yet obscured AGNs aren't just passive players in this model. They're smoking guns for black hole feedback. their buried radiation heating surrounding dust to hundreds of degrees, driving massive outflows that can sterilize entire galaxies of star-forming gas. Some even flicker between obscured and unobscured states, like NGC 5548, which over decades has alternated between hiding and revealing its core as dust clouds shift. These transitions suggest the obscuring material isn't static but dynamic, a turbulent, clumpy shroud that sometimes parts like theater curtains, offering fleeting glimpses of the monster within. The most extreme cases push obscurity to its limits. Hyperluminous infrared galaxies like ARP 2220 pump out 99% of their light as dust reprocessed infrared, their quasars so thoroughly buried that even X-rays struggle to escape. These cosmic furnaces hint at an explosive adolescence in galaxy evolution, where mergers funnel gas and dust into the core faster than the black hole can blow it away. The result, a self-cocooned AGN, its growth spurt hidden behind the very debris fueling it. What makes these hidden giants so pivotal is their sheer abundance. Surveys suggest obscured AGNs outnumber their unobscured cousins by at least 3 to 1, meaning most black hole activity in the universe is happening invisible to traditional optical telescopes. This hidden majority could rewrite our understanding of cosmic history, revealing that black holes spent much of their youth veiled, growing quietly behind dust before emerging as luminous quasars. The next generation of infrared and X-ray telescopes, like the upcoming Athena mission, promises to strip away more of this cosmic camouflage. With each newly uncovered obscured AGN, the universe reminds us, sometimes what you don't see is just as important as what you do. And behind every dark smear in the sky, there might lurk a monster waiting to be unmasked. Some quasars refuse to fade quietly into the cosmic night. Instead, they leave behind ghostly radio echoes that linger for millions of years after their visible light has vanished. These phantom remnants, like the enigmatic B20924+30, aren't just spectral oddities. They're time capsules preserving the violent final acts of once dominant black holes. What makes these dead quasars so haunting isn't their silence, but the way their whispers rewrite our understanding of AGN lifespans. B20924+30 was once a brilliant radio-loud quasar, its jets carving through intergalactic space with enough force to sculpt colossal lobes of plasma. Now its core has dimmed to near darkness, its accretion disk starved of fuel. Yet its radio lobes still glow faintly, their synchrotron radiation a fading echo of past fury. This afterlife phase, where a quasar's radio signature outlives its optical brilliance by eons, reveals a critical truth. AGNs don't shut down like flipped switches. They die in stages, their energy dissipating like ripples in a pond long after the stone has sunk. The physics behind these ghosts hinges on endurance. While visible light requires constant energy input to maintain, like a light bulb that dims the moment you cut power, radio emissions from jet lobes persist because the high-energy electrons trapped within them take millennia to lose momentum. Each spiral of these particles around magnetic field lines emits radiation, their energy bleeding away slowly like a spinning top gradually wobbling to rest. The result, a fossil record of the quasar's final explosive epochs, written in wavelengths invisible to human eyes but indelible to radio telescopes. But these ghosts aren't just relics, they're stopwatches. By measuring how much the lobes have faded and dispersed, astronomers can estimate how long ago the quasar turned off. B20924+30's lobes suggest its central engine sputtered out roughly 100 million years ago, yet its radio glow remains detectable. Similar structures, like the famed little Vorwerps, showcase ionized gas clouds still fluorescing from quasar light that has long since ceased, a cosmic version of seeing a room illuminated by a flashlight that's already been turned off. The most startling implication is scale. If radio lobes can persist for hundreds of millions of years, then surveys might be capturing snapshots of AGN deaths that occurred before dinosaurs walked the Earth. This forces us to rethink quasar demographics. What we classify as active or inactive could simply be artifacts of our limited time frame. A galaxy like B20924+30 might appear dormant today, but its lingering radio whispers prove it was once a titan, and that given enough time and a fresh influx of gas, it could roar back to life. Perhaps the most eerie detail is how these ghosts reshape their surroundings. Even in death, their lobes act as cosmic particle accelerators, seeding intergalactic space with relativistic electrons. Some studies suggest these ghost lobes might help reignite star formation in distant gas clouds, their residual energy triggering collapse in regions that would otherwise remain dormant. It's a paradoxical legacy, the corpses of quasars, cold and dark at their cores, still knitting new stars into the fabric of the universe. Yet for all their longevity, even these phantoms will eventually fade. As their electrons lose energy and their magnetic fields weaken, the radio glow dissipates into the quiet hum of the cosmic background. What remains is a galaxy subtly altered, its gas redistributed, its chemistry enriched, its structure shaped by the quasars' past outbursts. The lesson buried in these ghost images isn't just about endings, it's about transformation. A quasar's death isn't an erasure, but a transition one that leaves the universe forever changed in its wake. Quasars don't just light up the cosmos, they remodel it. The same ferocious energy that makes them visible across billions of light years can also sterilize entire galaxies, shutting down star formation with brutal efficiency. This cosmic sabotage, known as AGN feedback, turns thriving stellar nurseries into dormant, red and dead wastelands. And nowhere is this process more striking than in the enigmatic red geysers, galaxies caught mid-transformation by the unseen hand of their central black holes. Take the galaxy AGC 249525, a so-called red geyser drifting quietly through the universe. At first glance, it appears unremarkable, a faded collection of aging stars with none of the vibrant blue hues of newborn stellar clusters. But peer closer and its secret emerges, vast winds of ionized gas flowing outward at hundreds of miles per second, leaving behind a trail of heated, unsettled material. These aren't the gentle breezes of supernova or stellar winds. They're the fingerprints of a past quasar eruption, an ancient outburst from the galaxy's core that blasted away the cold gas needed to form new stars. The result, a galactic desert where star formation didn't just slow, it was suffocated. The mechanics of this quenching are deceptively simple yet devastatingly effective. As a quasar's accretion disk heats up, it unleashes two forms of feedback, radiative and kinetic. Radiative feedback floods the galaxy with high-energy photons, stripping electrons from atoms and heating gas until it's too agitated to collapse into stars. Kinetic feedback is even more direct. Ultra-fast outflows and jets plow through interstellar gas like cosmic bulldozers, either flinging it into intergalactic space or heating it to temperatures where star formation is impossible. Imagine trying to freeze ice cubes in an oven. That's the environment these forces create, but red geysers add a twist to the tale. Unlike galaxies fully quenched by past AGN activity, these systems show ongoing low-level feedback. Their black holes might not be quasars anymore, but they're still puffing out enough energy to keep star formation at bay. It's the difference between a wildfire and a smoldering campfire. Both prevent new growth, but one does it with lingering, patient heat. This slow roasting phase could explain why some galaxies stay dormant for billions of years, their gas reservoirs too unsettled to ever cool and condense again. The evidence is etched into their spectra. Red geysers exhibit unusually broad emission lines, a hallmark of turbulent gas, but without the bright blue continuum of active star formation. Their interstellar medium is caught in a purgatory, too energetic to collapse, yet too diffuse to ignite new stellar births. Surveys estimate that up to 10% of nearby galaxies might fit this profile, suggesting AGN feedback isn't a rare catastrophe, but a common, even expected phase in galactic evolution. What makes this transformation so pivotal is its role in the cosmic ecosystem. Without AGN feedback, massive galaxies would theoretically grow unchecked, their star formation rates soaring until they exhausted all available gas in a frenzy of supernova. Instead, quasars act like regulatory thermostats, their outbursts preventing galaxies from burning too bright too fast. In some cases, this might even extend a galaxy's lifespan, ensuring its gas isn't squandered in short-lived bursts but conserved over eons. Yet the story isn't one-sided. Not all feedback is destructive. In smaller galaxies or denser environments, AGN-driven winds might compress gas clouds at their edges, triggering new star formation in surrounding rings, a cosmic push-pull where destruction and creation dance in equilibrium. Even red geysers occasionally show pockets of residual star formation, hinting that feedback isn't an all-or-nothing switch, but a nuanced dial that the universe twists to balance growth and restraint. The legacy of these quiet giants challenges our assumptions about galactic life cycles. A red geyser's stillness isn't a sign of death, but of transformation, a galaxy sculpted by its central black hole into something slower, calmer, and stranger than its star-forming ancestors. And as telescopes probe deeper into the cosmos, they uncover more of these transitionary states, each a frozen moment in a billion-year saga of energy, matter, and the invisible forces that shape them. Hidden within the flickering light of some quasars lies a cosmic metronome, a steady, rhythmic pulse that could betray the presence of a hidden dance between black holes. Take PG 1302-102, a quasar whose brightness rises and falls every 5 years like clockwork. These aren't random fluctuations, they're precise enough to set your watch by, suggesting something far stranger than a chaotic accretion disk, an orbital ballet of supermassive black holes circling one another in the final stages before collision. What makes these periodic quasar clocks so mesmerizing is their potential to reveal black hole binaries, pairs locked in such tight orbits that their gravitational embrace distorts time itself. In PG 1302's case, the leading theory proposes a secondary black hole, roughly 100 million solar masses, whipping around its primary every 5 Earth years at a third the speed of light. Each orbit triggers a predictable surge in brightness, possibly as the smaller black hole plows through the primary's accretion disk, heating gas to white-hot intensities before slingshotting onward. It's a cosmic version of a spinning sprinkler. Each time the secondary completes a lap, it kicks up a wave of radiation visible across the universe, yet alternative explanations refuse to be dismissed. Some astrophysicists argue these ticks could stem from a precessing jet, a relativistic particle beam wobbling like a spinning top, periodically sweeping its spotlight across our line of sight. Others suggest lighthouse models, where magnetic instabilities in the disk create hotspots that rotate into view at fixed intervals. The debate hinges on subtle clues. If the brightness variations span all wavelengths evenly, it favors an orbital origin. If certain frequencies lag behind, it points to jet precession. PG 1302's clockwork precision, paired with multi-wavelength synchronization, tilts the scales toward the black hole binary camp, but the jury's still deliberating. What elevates this phenomenon from curiosity to cornerstone is its connection to gravitational waves. Binary supermassive black holes are the ultimate prize for observatories like LISA, future space-based detectors designed to catch space-time ripples from these collisions. The problem: mergers take millennia to complete, and catching one mid-spiral is like stumbling upon a ticking time bomb with eons left on the timer. Quasar clocks like PG 1302 offer a workaround. They're natural alarm systems, flagging binaries in their final centuries before merger. If confirmed, they'd give astronomers front-row seats to a process that shapes galactic evolution. The irony is delicious. The universe's most chaotic objects, quasars, might also be its most precise timekeepers. And as surveys discover more of these rhythmic anomalies, like the 8-year cycle of PG 1553+11, or the 16-month pulse of PSO J334+1340, they're assembling a catalogue of cosmic pendulums, each ticking toward an inevitable, universe-shaking convergence. Whether powered by dueling black holes or wobbling jets, one thing's certain: when a quasar keeps time this precisely, it's counting down to something extraordinary. Physics textbooks say there's a ceiling to how bright an object can be, a point where the sheer force of radiation blasting outward overwhelms the pull of gravity, stopping matter from falling inward any faster. This cosmic balancing act, called the Eddington limit, has long been considered an unbreakable rule for black holes, yet quasars laugh in the face of limits. Across the universe, astronomers keep finding these radiant monsters shining 10, 100, even 1,000 times brighter than theory says they should, blazing with energies that defy the very laws thought to govern their existence. The Eddington limit isn't just an abstract idea, it's rooted in straightforward physics. Imagine a black hole feasting on gas. As that gas spirals inward, it heats up, emitting enough radiation to push back against infalling matter. At a certain brightness, the outward pressure of photons equals the inward tug of gravity, creating equilibrium. Beyond that point, the radiation should theoretically blow away the accretion disk's fuel supply like a cosmic leaf blower, capping the black hole's growth. For a typical supermassive black hole, this limit works out to roughly 10 to the 38 watts, enough to outshine a galaxy. But quasars like S50014+81 don't just approach this boundary, they pole vault over it with ease. So how do they cheat? One possibility is sheer gluttony: black holes gorging on gas so fast they briefly exceed Eddington before the radiation can react. Picture a toddler shoveling candy into their mouth faster than their body can protest. The black hole's meal arrives in such a torrent that radiation pressure can't keep up. Simulations show these super Eddington phases might last centuries or millennia, fueled by dense, chaotic inflows during galaxy collisions or tidal disruption events. The quasar's brightness becomes a cosmic sugar rush, unsustainable but staggering while it lasts. But feasting alone can't explain the most extreme cases. Enter magnetic fields, the universe's ultimate escape artists. If a black hole's accretion disk is threaded with powerful magnetic fields, they might funnel radiation into narrow beams or channels, like sunlight through a fiber optic cable. Instead of pushing outward in all directions, the energy escapes along preferred paths, reducing the overall pressure on infalling gas. This flashlight effect could let a quasar appear obscenely bright from certain angles while technically staying below Eddington when averaged over all directions. It's a cosmic sleight of hand where geometry and magnetism conspire to hide the true cost of the black hole's appetite. Then there's the wild card: photon bubbles. Some models suggest that in super Eddington disks, radiation and gas don't interact uniformly. Instead, they separate into frothy structures, regions where photons escape easily alongside zones where gas slips through relatively unimpeded. The result, a leaky bucket scenario where radiation escapes without fully counteracting accretion. These bubbles might explain bizarre objects like ISO 243-49, a hyperluminous quasar whose energy output would require a black hole impossibly large under standard Eddington math. The implications ripple far beyond quirky outliers. If black holes routinely exceed Eddington, even briefly, it rewrites their growth timelines. Traditional models struggle to explain how the earliest quasars grew so massive so quickly. Super Eddington accretion could be their secret handshake. It might also explain intermediate mass black holes. the missing links between stellar remnants and supermassive giants by allowing smaller black holes to bulk up rapidly during galactic feeding frenzies. Yet the most tantalizing idea is that we're seeing new physics altogether. Could general relativity or radiation dynamics break down under such extreme conditions? A handful of theorists speculate about exotic processes like energy extraction from black hole spin or quantum effects near the event horizon that might bypass classical limits entirely. For now, these remain speculations, but every super-Eddington quasar is a data point whispering that the universe's rulebook might need a revision. The Eddington limit isn't just a line in the sand, it's a frontier. And quasars, ever the rebels, are dragging us kicking and screaming across it, forcing us to confront how little we truly understand about the most energetic engines in existence. Their brilliance isn't just light, it's a challenge written across the cosmos in photons, daring us to rethink the impossible. Quasars don't just blaze with raw energy, they act as cosmic lighthouses, their light piercing through the darkness between galaxies to reveal the universe's hidden scaffolding. Imagine shining a spotlight through fog. The beam not only cuts through but also illuminates the mist itself. That's precisely what quasars do on a galactic scale, their radiation traversing billions of light years and picking up fingerprints from everything it encounters along the way. The key to this celestial detective work lies in absorption lines, the dark gaps sliced into a quasar's spectrum by intervening gas clouds, each a clue about the composition, temperature, and even the motion of material we'd otherwise never see. Take the Lyman alpha forest, a bizarre pattern of absorption lines found in quasar spectra. These lines betray the presence of neutral hydrogen gas strung along the cosmic web like dew on a spider's silk. Each dip in the quasar's light corresponds to a specific cloud at a specific distance, creating a layered record of the universe's structure. The closer the lines crowd together, the denser the gas, the more they're redshifted, the farther away they lie. It's as if quasars are cosmic sonar devices, pinging their way through the cosmos and mapping the invisible with every photon. But the revelations don't stop there. Heavy elements like carbon, oxygen, and iron detectable in absorption shouldn't exist in intergalactic space at all. They're forged in stars and dispersed by supernova, yet quasar spectra show them peppered far beyond galaxy borders. This enigma suggests explosive galactic winds, powered by quasars themselves, have been scattering metals across unimaginable distances for billions of years. The universe, it seems, is far more interconnected than we ever imagined, with quasars not just illuminating the void but actively seeding it with the building blocks of planets and life. Even dark matter, the universe's most elusive substance, leaves subtle traces in quasar light. While dark matter doesn't absorb photons directly, its gravitational pull distorts the paths of background quasars through weak gravitational lensing. By studying these minute deflections, astronomers can chart dark matter's distribution in the cosmic web, revealing colossal filaments and voids that span millions of light years. Quasars become backlights for the invisible, their flickers and bends exposing the hidden architecture of reality. Perhaps most astonishing is how these beams of ancient light double as time machines. A single quasar spectrum can contain absorption features from gas clouds at dozens of different epochs, each layer a snapshot of the universe at a different age. By comparing quasars at varying distances, astronomers have reconstructed the universe's chemical evolution from the pristine hydrogen of the early cosmos to the metal-rich tangles of today. It's like flipping through a photo album where every page shows the same scene at a different stage of development, revealing how chaos gradually gave way to structure. Yet quasars don't just passively illuminate the cosmos, they transform it. Their ultraviolet radiation ionizes intergalactic hydrogen, stripping electrons from atoms in a process that shaped the universe's transparency during the epoch of reionization. Without these beacons, the cosmic dark ages might have lingered longer, delaying the birth of galaxies and stars. Even now, quasars continue to sculpt their surroundings, their light dissecting gas clouds, tracing dark matter, and chronicling the universe's growth with unmatched precision. In the end, quasars are more than just brilliant oddities. They're the universe's ultimate probes. Their light carries stories of everything it touches, from the faintest wisps of gas to the mightiest gravitational fields. And as we decode these messages, we're not just observing the cosmos, we're reading its diary, one luminous line at a time. Quasars and active galactic nuclei aren't just cosmic oddities. They're the universe's ultimate laboratories, bending the rules of physics and rewriting our understanding of reality at every turn. From the mind-bending illusion of superluminal jets that appear to outtrace light itself, to the rhythmic ticking of binary black holes counting down to collision, these phenomena stretch the limits of what we thought possible. They flicker like cosmic strobe lights in Blazars, leave spectral double-peaked calling cards, and even play hide and seek behind redshift anomalies that defy explanation. Some outshine entire galaxies while others lurk in dusty shadows, their brilliance filtered through cosmic veils. They sculpt galaxies with hurricane-force winds, echo their past outbursts across millennia, and occasionally vanish overnight only to roar back to life without warning. The sheer diversity of these 25 phenomena reveals a universe far wilder than textbooks could capture. Magnetic fields twist into cosmic tornadoes, spinning black holes launch jets that drill through intergalactic space, and entire galaxies glow green with the afterburn of quasar radiation. We've seen quasars act as cosmic clocks, their periodic pulses betraying hidden duos of supermassive black holes in gravitational tangos. We've watched them defy the Eddington limit, shining with impossible brilliance as they teeter on the edge of physics itself. And through microlensing, we've glimpsed their inner structures, hotspots and spirals in accretion, disks too small to image directly. But every mystery solved unveils 10 new questions. Why do some quasars align with the cosmic web while others ignore it completely? How do black holes flip between radio loud and radio quiet states? What triggers the violent rebirths of changing-look quasars? Each anomaly is a breadcrumb trail leading deeper into the unknown. These aren't just academic puzzles, they're clues about how galaxies form, how matter behaves under extreme conditions, and even how the universe itself grew from primordial chaos into the structured cosmos we see today. So here's the real question: which of these quasar mysteries grabs your imagination? Is it the ghostly green bean galaxies glowing with fading radiation? The rogue quasars that appear disconnected from their host galaxies, or perhaps the super Eddington monsters breaking all the rules? The comment section is your launch pad. Share which phenomenon makes you stare at the night sky and wonder. Because the wildest part isn't what we've discovered about quasars, it's what we haven't found yet. The universe is still writing this story, and every observation could be the key to the next cosmic revelation.